Good day and welcome to the Math Salon. I'm Dr. Anumendem. Today we'll be looking at a question on matrices, 3 by 3 matrix, to be able to look for the determinant and the inverse and possibly use it to solve a system of linear equations. So here the question says that given that the matrix P is 1, 0, 1, 2, 1, 1, 3, 2, 3, find the determinant, the inverse, and solve this system of equations. So to get the determinant here for a 2 by 2 is very simple, but for a 3 by 3 we have to be a bit careful. In order to get the determinant of a 3 by 3 matrix, you are free to choose any row that you want or any column and expand. There are many other techniques to do that. We will choose one that is, I think, is simple. So what we do is that you first try to make sure you assign the position of the elements. The first one is always plus, and then the sign alternates. So this is plus here, this is minus, this is plus, this is plus there, this is minus, this is plus, this is minus. And we will use those signs when we are computing our determinant. So I would expand across the first row there. I'm choosing the first row because it has a 0. So it is best if you see a row, a column that has a 0, that you choose that one. It's much easier. So in this case, what I do is that I get 1. When I take this one, this is the one written here, and it's a plus, so it's plus. Then I remove the column and the row containing 1, and the submatrix that I have, I get the determinant. So this is 1, 1, 2, 3. Then I go to the next element, that is 0. It's minus, so that's minus 0. And I remove the column and the rows containing 0, and I get 2, 1, 3, 3. And I get that plus 1. This is 1 there. I remove the rows and columns containing 1, and it's a positive. So I get 2, 1, 3, 2. 2, 1, 3, 2. Once that is done, I'm left just to compute this determinant of 2 by 2, which is much more easier. So this is 3 times 1 is 3 minus 1 times 2, that's 2. And this is 0, so it doesn't matter what comes out of this determinant, it will be 0. And this is 1 again, so 2 times 2 is 4. 4 minus 3 is 1. So I have 1 here, I have 1 there. 1 plus 1 is 2. We are done with the determinant, it's 2. So we go now to the inverse. The inverse is defined as 1 over the determinant of the matrix times the adjoint or the adjugate of P. Yeah. So the adjoint or adjugate is simply the transpose of the cofactor matrix or the cofactor matrix of the transpose. If you do any of them, you should come up with the same result. So what I would do is that I would first transpose the matrix P. So this is my matrix P. I would transpose it. To transpose a matrix simply means change all your rows to become columns or change all your columns to become rows. I will do the earlier one. So I will change all my rows to columns. So I have 3 rows here. So the first row is 1, 0, 1. If I take it here, I can rotate it and it becomes 1, 0, 1. That is now a column. 2, 1, 1 is a row. When I rotate it becomes 2, 1, 1. 3, 2, 3 is a row. When I rotate it becomes 3, 2, 3. So this is my transpose matrix of P. It's left now to formulate the cofactor matrix from this one. Once again, we'll apply those signs that we talked. They are in red, so they don't affect the number itself. They are signs for the position. The first one is always plus. If you know that, then the rest will come because they just alternate. So it is plus, minus, plus, plus, minus, plus, minus, plus, minus, plus, minus. So what we do is we do something similar to that, just for the fact that we will not use the elements themselves. So for example, 1, the cofactor of this one here is you remove the column and the row containing 1, and it's simply the determinant of the matrix that is there, taking into account the sign of the position. So in that case, I have 1, 2, 1, 3, and it's a plus. We go to 2. 2 is a minus position, so I have the minus. I eliminate the column and the row containing 2, so that is 0, 2, 1, 3. 0, 2, 1, 3. I come to 3. 3 is positive, so it is plus. I delete the row and the column containing 3, and the remaining is 0, 1, 1, 1. 0, 1, 1, 1. I come to the second row. I look at this, the sign is minus, I put the minus there. The row and the column that don't have to contain the 0 will be 2, 3, 1, 3. 2, 3, 1, 3. I go to the next one, I remove the column and the row containing that, and I get 1, 3, 1, 3. 1, 3, 1, 3. Come to this one, it's a minus, so there's a minus there, and I remove this row and the column containing it. What is left is 1, 2, 1, 2. 1, 2, 1, 1, excuse me. If you remove that, is 1, 2, 1, 1. So this 1, 1, 2, 1, 1. And I come here, I do the same thing for this. It's a positive position. Then I get here, I remove that, I'm left with this. 2, 3, 1, 2. I do the same thing here. So this is that. I remove this row and column and I get 1, 3, 0, 2. And the same thing for the third one, and you come out. So this is the cofactor matrix of the transpose of P, and that's what we call the adjoint or adjugate of P. Once we simplify this, we can put it here and get our inverse. If we simplify that, we see, for example, 3 times 1 is 3 minus 2. So that's 1 here. 3 times 0 is 0 minus 2, and the minus outside becomes plus. 1 times 0 is 0 minus 1 is minus 1. This plus outside. The side remains. I do the same thing for the rest, and I will get minus 3, 0, 1. And below here as well, so this 2 times 2 is 4. 4 minus 3 is 1. That's the one there. 1 times 2 is 2. 0 times 3 is 0. So 2 minus 0. But with the minus there, it becomes minus 2 and 1. So I have my adjoint of the matrix P. So the inverse is simply 1 divided by the determinant, which we already had here as 2, multiplied by this matrix that we have here. Now we have this system of equation to solve. Of course, this is the way it was given here. I just made an arrangement. You see, there is no y here in the first equation. So I will just imagine that there is a 0y. It's good to do that so that your matrix has a very good structure and you'll be able to pick the elements. So if I do that, then I have x plus 0y plus z is equal to 2. 2x plus y plus z is equal to 0. And 3x plus 2y plus 3z is equal to 1. If I arrange this in matrix form, then I come up with this, where these are the coefficients of my variables x, y, and z. So this is 1, 0, 1, 1, 0, 1, 2, 1, 1, 2, 1, 1, 3, 2, 3, 3, 2, 3. And of course, I have to write my vector x, y, z, so that if I do multiply, I get back exactly what I did. So from here to here, it's just some cosmetics. This is the math salon. So if we do that, then this side becomes my constant matrix. So it means I can write this as a matrix P multiplied by matrix X is equal to a matrix C. So if I want to calculate X here, then yeah, in normal mathematics, you would just say I divide both sides by 2 or divide by P and P cancel. But this is a matrix, you cannot just divide by P. So we multiply by P inverse. We do that on both sides so that our equality stays. So P inverse times this side must be equal to P inverse times this side. The P inverse times P is an identity matrix, I. And the identity matrix doesn't change the matrix that it multiplies. It leaves it the same. So if we do that, then I get this from here. What I'm left now to do is just take my inverse that I calculated before and multiply by C. And this is what we'll do here. So my inverse is 1 over 2 times that there. And we will just multiply with this. If you do that, you will get 1 over 2, I just keep it outside, I don't lose anything. So 1 times 2 plus 2 times 0 plus minus 1 times 1. So if I do that, I get here 2 minus 1, and that is 1. Minus 3 times 2 is minus 6. 0 times 0 is 0. 1 times that is 1. So minus 6 plus 1 is minus 5. 1 times 2 is 2. 2 times 0 is 0. 1 times that is 1. So 2 plus 1 is 3. Of course, I have a half outside, so I can multiply each element of the matrix by that scalar factor. So I get here 1 over 2 minus 5 on 2, 3 on 2. And each of them correspond to the x, y, and z in the corresponding. So x is equal to half here, y is equal to minus 5 on 2, and z is equal to 3 on 2. That is it for this question on matrix. Thank you once again, and remember to give us some thumbs up and please subscribe. Have a nice day. Bye-bye.